Our next speaker is Professor Luca from MIT. Luca had his PhD from UC Berkeley in 2003, and Luca has been working on many research areas spanning from numerical techniques to deep neural network-based applications. Today he's going to talk about how to quantify the lack of robustness in deep neural networks. Let's welcome.
Thank you, Sija, for the kind introduction. So first and most importantly, I would like to acknowledge the very crucial contributions of my senior graduate student, Sui Wei Lili. Lili could not be here. She's traveling internationally. I really wanted her to be able to present her work. I would also like to acknowledge the precious contribution of my collaborators at IBM. Sija is one of them, Pinyu, a lot of other collaborators, students, colleagues, funding from IBM AI Lab and MIT Quest for Artificial Intelligence. I have to apologize, I could not attend the beginning of this session. What I have to say, I'm guessing, is not going to be that different from what some talks had to say at the very beginning. I have seen my colleague Alexander Magri giving fantastic talks before. I have to say that I agree on everything that he says, and you probably recognize a lot of the things that he said in my talk. That is to say that, it's the last session, it's the last talk. I will not be offended if you decided to start your weekend early. I've also decided to target a different audience, at least a different audience that what I've seen done in other talks at this conference. A non-technical audience, because as you can see, my title is a question. And I think that when it comes to this topic, the questions are more important than the answers. And that is because I myself, my group, and probably a lot of people in the community, if not all of us, still don't have very clear answers. So I'm going to keep it high level. It's also good because right before lunch, a lot of math might be problematic. So here's our good friend, the neural network, a collection of neurons with weights and activation functions that you can use to do pretty much anything these days. But for example, they can be used to do image classification. We know that performance gets better and better the more training data you have. We've heard this a million times. Here's one more time from me. But how many times did you stop thinking about what it means performance? What people actually measure? A lot of my talk is about what should we measure. So what typically is measured is the number of errors or the percentage of errors, especially when compared to what a human could do. And maybe 20 years ago, things were not going very well for neural networks. Yes, they've been around for 20 years for those of you that were not born at that time. Maybe a human could do 95% accuracy, meaning number of correct guesses or classifications out of 100. And a human network and a neural network might be able to do only 30, 40%, 50, I don't know, something like that. Things kept getting better and better. Eventually they saturated. I apologize for the contrast here, not very visible. But again, fortunately, if you're an optimistic, maybe not so fortunately, if you're like me, more of a skeptical person, things started getting better again. So much better, meaning again, number of errors or percentage error, that we started getting better than humans. So out of 100, a very highly performant deep neural network could, for example, get 99 things right, just make one mistake. A human still 95%, so 5 mistakes. So what do you choose? Well, of course, we choose the deep neural network for any of our decision making from now on. So they are quickly becoming what I would call our hero. The neural network is coming to do everything for us, as I was mentioning before, from image classification to object detection to natural language processing. So we're already, most of us are dreaming to having them drive our cars, hire our people, invest in the stock market for us, so on and so forth. But I would like to bring back the question that I mentioned before. What does it mean to be better? And what I mentioned before is something that will highlight a dark side of our hero, potentially. Or at least, let's have some questions about this. So what we count is the number of errors. But do we ever stop and look at those errors? I would like to stop and look at those errors. So, for instance, yes, it's true that this very highly performant deep neural network make very few errors. But, well, I don't know, that one error that they make, maybe that's a very difficult case, and no human would ever make a good classification on that specific input. Okay. Or maybe there are very few humans that would be able to guess it right on those specific cases that a deep neural network get wrong. But how would you react right now if I were to give you examples of errors that the deep neural network makes very highly performant, and no human on Earth would ever make an error on that specific input? Specific input is the key word here, specific input. So we should actually try to look at those. And also, how about, okay, maybe we just stick with errors that both the deep neural network and the human make. Can we look at how big those errors are? So what if a human, yes, makes an error, but it's not that big, while a deep neural network makes a huge mistake on that specific case? How would you react in that case? What would you prefer? These are questions we should ask, and they go beyond math, in my opinion. All right, so let me start digging in and show you some images. You probably, if you are in the community, you've seen all of these images, and you've seen where I'm going. If you were in a Madrid talk today, you know where I'm going, but don't need to answer. Just answer to yourself what you think this is. I'm guessing that a lot of you might conclude this is an ostrich. Good for you. The first time I saw it, I wasn't really sure, maybe because I'm not a native speaker. It's about the language as well, but definitely I was able to conclude it's some kind of bird. And no question in my mind, and most likely no question in anybody buying in this audience, this is at least an animal. Well, good for us. The highly performant deep neural network agrees completely with us and extremely confident tells us it's an ostrich. What about this one? Well, if you ask me, I would tell you, well, now that I learned that that's an ostrich, this is an ostrich too. Actually, it seems like it's the same ostrich to me. How would you react if I told you that that same highly performant deep neural network that gets fewer errors than humans tells me it's a unicycle? Particularly concerned about the fact that it's not even the mistake this neural network makes. This superhuman deep neural network makes a mistake. And it makes a mistake that is not even another kind of bird. It's not even an animal. It's a unicycle. It's not even an animal. So I'm upset about this. I'm also upset about the second thing. If you look at the last neuron, the last layer that is responsible for this assertion, corresponds to an ostrich, it's happily firing, extremely confident, just as confidently as before that that's an ostrich. And to me, there's nothing worse when you're trying to build trust than someone who says something wrong extremely confidently and thinking they're right. That's very upsetting. Or at least it doesn't make me want to trust that thing or person or whatever that is. All right, I said a lot of negative things about deep neural network. It's about time I say something positive. So let me try to defend this. Well, this is the very, very clever work of some extremely gifted hacker that had managed to get information, inside information on that specific deep neural network, and knows the structure, knows the number of layers, knows the coefficients, knows everything about that neural network, and is able to exploit very cleverly all of those things. This is called an attack. All right, so it's not something that happens every day. You need a hacker that has all of this information. This means that the people that started worrying about this are the security people, because there's an attacker, there's a hacker, and they started thinking about what can happen. For example, if your self-driving car gets hacked and it doesn't recognize stop signs anymore, is someone trying to kill you or something? Well, this could be one way. Unlikely, but possible. What if your Siri doesn't recognize what you're saying? Because a hacker, again, gets in and has access to everything inside the deep neural network of your Siri phone or whatever you're using. People started designing glasses that you can wear, and deep neural network will think that this man here is actually this woman over here, just because they're wearing that special glasses. Students here at MIT were able to take a living animal like this turtle and just paint something over it and make deep neural network think that that's confidently a rifle. So it's not just an image problem where you change a few pixels. All right, so this feels like it's a serious security issue. Yes? Let me bust a few myths for you. Point number one, that hacker that I mentioned before needs to have complete access to the inside information on the deep neural network actually does not need to have complete information on the neural network. Does not need to know anything at all about that neural network. And some of my collaborators showed that you can just look at that neural network as a black box and just be able to ask questions and get answers is enough to synthesize a picture like this. To me, looks like there are two guys happily skiing up in the mountains. There's no question to me that that's what this picture represents. But then I look at the deep neural network, and there's a neuron there corresponding to dog that says 91%, higher than all the others. They had no information about how that neural network was trained, what data set was used, what the coefficients were, what the structure was. Just ask questions. All right, now I'm getting a little more concerned because it's not enough to protect the inside information on my network. Let me bust a second myth for you. I don't even need the hacker. I don't even need that very skilled person. There are very few in the world, and they're all in this community of trying to hack neural networks, and they're very smart, much smarter than I am, and they're capable of doing this. I don't need them. Things are a lot more serious than that. Because people have looked inside ImageNet, the database of existing images, and you can find images that have not been hacked by any hacker, any gifted person with this insane ability of doing these things. And they were able to find pictures that this highly performant deep neural network, the one that has superhuman performance, the one that gets 99% of the answers correctly, more than a human would do, that's the same neural network that tells me that this thing here, number 3, for example, it's a pretzel. Yeah, I see a mushroom. I might not know what kind of mushroom, but I do see a mushroom. This is not a butterfly, apparently. This is not a squirrel. Yes, I don't know that it's a fox squirrel, but it's a squirrel. It's not a sea lion. So hopefully you're starting getting concerned. This is why I said that sometimes asking the question, or actually having you ask the questions, is more important, because what I want to do is have more people that ask these questions, because all of us can hopefully find better answers for the community, rather than focusing on me giving answers to some of these questions. So this is particularly concerning to me because it moves outside of the realm of just security. There's no hacker anymore. There's no malicious attacker. There's no getting possession of inside information of your network. So if you are considering, planning, or dreaming about handing over your decision-making to deep neural network, you better start being concerned about safety and fairness, for example, issues. Especially, and here I have to make a distinction, of course, because if you're asking your deep neural network to make decisions about things that have no consequences, you're trying to do specialized individual pricing and ask me different price for priority boarding and privilege of getting my seat before others, who cares if you misclassify me? What's the worst thing that can happen? I'm sitting in the back of the plane in the middle seat. I can live with that. It changes if there are really substantial consequences to the mistakes of this network. And I don't care if the number of mistakes is smaller. I get particularly concerned if it makes a mistake on something that no other human on Earth would make a mistake on. That's what I get concerned about. And the mistakes they make is much, much larger than any human would do. Topics, actions, things like autonomous driving, insurance-influenced medical treatment selection, employment hiring decisions, prison probation approval, pricing for large equity, mortgage, life-changing decisions. Let's be careful as we move into handing over decision-making to deep neural network when we're talking about very big consequences on errors. All right, so what can we do about it? This is topic for research for a whole community, in my opinion. And my goal here is just to get more and more people interested in doing research here, because we need a whole village of people working on this. I'm going to start small. I'm going to mention a few things that we are doing as just part of a big village, and the whole session today showed all of the really valuable and very important contributions that our people have been doing. To me, for example, if I need to start building trust on someone, let's forget deep neural network, even a person that talks to me, the very first necessary condition, not sufficient, just necessary, but starting point, is that, well, this person better know and better be able to say what they don't know if they want to start building any chance of trust from me. So for me, raising awareness is particularly important, especially when you are planning about using deep neural network for decision making. And one of the things that we started doing, or a whole community of people started doing, is start defining what it could mean to have a lack of robustness, define and maybe develop tools that measure it and quantify it. So the goal, the dream here, is to have a tool that runs parallel to the deep neural network, and it's about the same time. Will be able to tell me also something about how confident that answer is. And I'm not just talking about reading the value of the last neuron that says 91%, because we decided that's really not the value of confidence. Something else, what if I start perturbing my input, like many people said today in this session, all of a sudden the answer changes. If I see that that happens, maybe that's not trustworthy. How large of a perturbation do I need to make before the answer changes? Well, if I need to make a large perturbation before the answer changes completely, maybe that's just a starting point for building the trust. It doesn't mean that I'm going to trust. So that's the goal. Hopefully, this tool will be able to raise a flag, produce some warning for a small number of cases, so that hopefully in that case, the human is still there being called up to look at that specific case. There are not many, fortunately, because our highly performant deep neural network are so good that they get it right on so many times. Great, so let's look at those mistakes and let's really have something else involved in those mistakes, hopefully. So let me proceed now in this direction of trying to develop ways to measure and quantify this amount of perturbation. And I'm going to give you first a graphical representation, then I'm going to give you a little bit of math, but really I'm trying to stay away from math, because the more math I give you, the more you lose track of the key point, which is the questions. So if this is an ostrich label, and maybe that's associated with a specific vector, which has maybe all the amplitudes of the pixels on this picture. This happens to be a very large dimensional space, which I cannot represent on this slide, so it's actually a point in a 2D space. I apologize for that. There might be a decision boundary, and across that decision boundary, I might have another label. Maybe it's a chicken label. And there's many decision variables. This is actually not to scale. Imagine there's maybe a lot more space, and things are closer or farther away. We're also in 1,000, if not million dimensional space, so there's millions of these decision boundaries around. It's not so easy as it looks in this picture. So if I start modifying this picture, I might end up somewhere close to the boundary, maybe just across, with something crazy looking like that. I'm sure that a lot of you that are in GAN have learned to appreciate the beauty of these crossed animals or things. This is actually not, I don't know if it was generated by a GAN or whatever. I just searched on Google ostrich chicken and look at whatever came out that looked strange. I have no problem with this. This happens all the time. Somewhere in between there, you're going to have with something that even a human cannot tell. And actually, I have no problem with this because a lot of times deep neural networks also have a problem with that, and they tell you they do have a problem. In this case, maybe it's firing 55%. That's not my issue. My issue is the existence of other situations, and here I'm just showing the amount of perturbation on an axis so we can keep track of it. A smaller perturbation, so that I end up with something looking like exactly the same picture as before, so tiny perturbation that I cannot tell the difference. Now it gets classified really, really, really confidently as a vacuum cleaner. That's what I have a problem with. On these boundaries, there are situations like that. They're not very common, but they can exist, and people have shown the existence. They're called attacks, like I mentioned before. So let's put that distance here on this plot, and now let's look for this ball. A lot of people mentioned balls today, and here I am showing this other representation of exactly the same thing. How large of a perturbation do you need to get to the closest boundary? And if we can measure that, that's possibly an indication for how much robustness you might have in the perturbation of your specific. This is specific. It's input specific. There's not a single ball that works for all the inputs. Every single input has its own ball because it might be closer to a nearby boundary. That's very important to keep in mind. So it turns out that this can actually be measured, but it turns out it's extremely expensive to do it exactly. People have done it. There's this Reluplex algorithm that does it for you. On a very small network, 300 neurons. What can you do? Think about what you can do with 300 neurons. Not ImageNet. It takes 3 hours. So this is far from my goal of running the deep neural network assessment and then running also this tool in parallel and getting a level of confidence. A decision maker might not want to wait these 3 hours. So if you start thinking about what you should do as a research, I mean, improving the speed for the evaluation of these whatever measures or scores for robustness is a great thing to do. So Lily is my graduate student who started looking at these issues, and one of the first things that she did is try to find some theoretical result that linked this radius of this ball, minimum perturbation, and p norm, to the closest boundary, and she was able to relate it to the Lipschitz constant without going too much into details. I promise no math, and here I am showing a math. I couldn't resist. But if basically you start thinking very, very intuitively, please apologize for the people that are technical in the field, but something about steepness of the activation functions, and high steepness, very, very steep activation function seems to be a bad thing from what we've seen. And I have developed some kind of intuition for why that might be the case. Maybe I don't want to say it yet on a video recording, but you can ask me later. So once she has established this theorem, the next question is, how do I actually compute this value? So the first thing that she did is, oh, let's just use some sampling, for example, and let's sample around the ball and try to get an idea for how large that is. Let me emphasize, and I put it in red, that, oh no, I didn't put it in red. I'll put it right on the next slide. This is an estimation of that ball. Estimation means that you accept the risk that it might be incorrect. So let me show you how well it works, and let me show you also why sometimes it doesn't. Because if I want to build trust, I need to show you what I don't know and when things don't work. So these are different databases with different examples. There are different attacks. So this is the amount of perturbation that these specific attacks needed to impose in order to get a misclassification that look very much like the same image to a human, because these are very small numbers, very small perturbations. This score here, the clever score, is Lily's score in terms of using sampling and extreme value theory to try to get an estimate for that number. And they're similar, so we're happy in terms of that. They are supposed to be smaller because you're trying to estimate the minimum perturbation before you get a misclassification. And they are always smaller, similar, except for at least this case that we were able to find. And we looked for it on purpose because I knew it was going to happen, and there it is. Where in this case it's slightly larger. So that shows you that it is an estimation. So it gives you an indication. It's something that you can use it to raise a flag, warning, warning. It doesn't mean anything else, but just be careful and look closely with other tools to that specific input. So the next thing that she did, and a lot of people did in the literature, and I'm really happy that this is moving in this direction, is what if we give up some of our desire to estimate the exact number, and we try to look for a more conservative number, maybe even 2 or 3 times smaller radius, but we guarantee it. It's a lower bound. That's also an interesting direction for research that I encourage people to take, and Lily also moved in that direction. So that was the estimation. I'm trying to progress some history here on things, and she started looking into this robustness certification, which is basically trying to find this lower bound guarantee. And because this robustness seems to have to do with steepness and slope of these activation functions, then she started with very simple activation function that had only 2 slopes, flat and another slope, the ReLU. And in that case, she started bounding locally each activation function with 2 linear bounds, the same up and down, and then propagating them through and making the epsilon, the perturbation, larger and larger until you get an overlap. Don't want to go too much into details. There are many things that I want to mention, but the bottom line, I think looking at how well it works is probably more interesting. I'm showing here small examples. These are small examples, 2 layers, 20 neurons, 4 different norms, different ways of measuring that ball. As a reference, what did we use? Of course, we use ReLuplex. It can be done because these are small examples. Remember, it's expensive. Maybe it takes 3 hours just for running one of them. It can be done only for infinity norm, not for the other p norms. So for those, we had to look for other references. For example, this linear programming approach, which doesn't give you the exact value, but it gives you a lower bound and a decent one. Maybe it's far off a factor of 2 from the actual value. And her technique that I just described before about producing linear bounds on activation functions and propagating them does pretty well compared to that. Pretty much for a lower bound that gives up a factor of 2 to 4, meaning that 2 to 4 is a smaller radius of the perturbation compared to the exact number, she was able to complete the computation in a time that is 12,000 times faster than ReLuplex. And maybe for a similar number in the bound as LP, she was able to do it 2 orders of magnitude faster. For 3 layers, things get better. 6 million faster than ReLuplex, 1,000 times faster than LP. Speed is important, right? Remember the goal. We need to provide something that you can run in parallel to your neural network so that for each point you run, you also get a really better indication if you can trust it or not. So in summary, well, it does good quality of the bound close to LP result, much faster. What happens if you start scaling and go even higher? Well, we were able to go up to 7 layers, 1,000 neurons for each layer, which is larger than that, but definitely not at the scale of ImageNet. And this is where a lot of research, in my opinion, needs to happen. Because right now we are about maybe 10 to 15 seconds, which is the time it takes to certify a specific answer and give you a very good indication, a lower bound certified for the amount of perturbation you can afford before you have a potential misclassification. So it depends on what is my goal here, and what I'm making a decision on. If I'm making a decision on boarding priority, I couldn't care less. I mean, really. But if I'm making a decision about diagnosis, I'm making a decision about something more substantial, I'm definitely willing to wait 10 seconds to verify, even more than 10 seconds, in my opinion. So she chose to move in a different direction. Instead of improving speed, which I think needs to happen, she started expanding the technique with other collaborators in the group to other kind of activation functions, more generic activation functions. Instead of using the same linear bound for below and above, she started propagating 2 different bounds. That seems to work. And then you can handle different kind of activation functions. Then a really brilliant undergraduate student, I'm so happy. Undergraduate students are contributing to research in this field in a way that I've never seen in my career before. I've been in many fields. And undergraduates, all it takes is to be smart to be in this field. This is a good thing for the field. So let me introduce you to Akilan here. Akilan was able to extend these results, producing bounds, certified bounds, to convolutional neural network. And instead of propagating this linear bounds, since we have a convolutional neural network, he tried to use convolutional type of form for the bounds. I want to keep it short, so I'm going to move very quickly to final remarks. First of all, I'm really happy that the community is finally beginning to understand the issue, that there is a question, and start looking into measuring robustness. There's a lot of people that have been producing very interesting measures. I'm also very happy that the people outside of our community are beginning to understand the issue, because our community has to reach outside. It's extremely important, because the decision makers that are considering using deep neural network to make their decisions are not experts of machine learning. And this is my problem, when they don't know anything about all of these things that are going on inside, and they want to trust them completely. That's where I get concerned. So I'm really happy that people outside the community are beginning to appreciate the fact that there are situations where things might not be as nice as we would like them to be, and there is more research that needs to be done to improve that. I'm also very happy that the community is beginning to develop tools, because this is absolutely needed, in my opinion, that can help these users not only get an answer, but also get an assessment for how much they can trust that answer. And IBM has been doing a great job, has been a fantastic collaborator in terms of doing this, because they've been developing tools in parallel with us, with these papers that are being publishing, and deploying these tools for people to use, where you can quickly assess and get an idea and get a flag, a warning. Is this an answer I can trust, or do I need to think harder about this specific input? All right, so let me summarize. For me, very important to raise awareness that there are some potential issues. The definition of performance is something that I hope you understood. It's not a single way of measuring that we need to look at. There are many more ways of measuring. We started defining robustness, for example, looking at the size of perturbation. I welcome many other definitions. Please, everyone that is involved or wants to get involved, there's a lot of space here. Very important that you also think about computing it fast, whatever you do, because otherwise users will not use it, and then you defeat the purpose. And most importantly, I think I would like, there's one thing that deep neural network, even the highest performing deep neural network, haven't learned to do yet. And they really need, in my opinion, to learn to admit what they don't know or what they might not be sure about. That's my final message. Thank you.
For those national scenarios, advanced scenarios, do you have any idea what Vietnamese classified is the background of this? You showed some of those images.
Do I have an idea for how these... there's a whole community of attackers that have pretty good ideas on how they actually do this, and it's a variety of reasons. Some of them, for example, have to do with the fact... yes, I said before that I wouldn't say it publicly. Maybe I say, well, when people do training, for example, what do? They typically use activation functions with very small slopes, because it's easier to train, because you always know which way to go. But those produce networks that don't give very clear answers. They give you 55, 57, 60% firing. Users love to see 91%. So what they do is, once they're done, almost done training, they increase up those slopes of the activation functions, and they make them much steeper. So that means that all of a sudden, something that was maybe firing at 60% is now firing at 91%. So that means that sometimes we're doing it to ourselves. Now we have a network that answers more confidently, but that means we expose it to also making more mistakes on things that shouldn't be answering so confidently. There are other mechanisms. There are mechanisms where, for example, the attackers exploit part of the image that we as humans are not sensible to. So it could be that you look at the spectrum, the frequency components that we're not used to or not capable of looking at very easily. You can hide these variations in different places. There are situations where deep neural network maybe recognize that one specific animal might have a specific feature, and only that animal in all those millions of pictures, only that animal has that specific feature. If it recognizes that, it's going to look for that specific feature only, and if it finds it, it says that's that animal. Now, if that feature is, for example, I don't know, a triangular ear, and there's only one animal in the world that has that, what happens if there's another animal that gets in a fight and someone is biting off a piece of the ear and then it ends up being triangular? The neural network will see the triangular ear, will say, oh, it's an ostrich. No, it's not. A human would not say that. It would say, it's a dog with an ear that has been bitten off. So there's so many failure mechanisms. The more I look into it, the more I discover more. It's like making a list of all these failure mechanisms is not the way to go, in my opinion, because there will be always more and more that people can find or people can invent. This is why I decided to not even get into that fight. I just got into let's measure the robustness. Let's try to provide an assessment.
Yeah, I guess my question is, I mean, those images are very interesting, like the natural, actually, together misclassified. So I wonder if people have started looking into, what are the differences between those images and those machine manipulated images or machine prepared images?
There are people looking at them. Yes, there's different ways to plot. You can just look at the noise that was applied. You can try to look at which neurons are firing more or less. You can do maps of which neurons are responsible and what they're looking. You can see what the neural network is looking at in the picture and do a heat map to understand what made it, or where at least the problem might be. I am trying to be vague on purpose because I don't have answers myself, and I don't think that all of these people that are looking at these answers have already answers. These are tools that they're developing to try to get to answers and understand. But that itself, to me, is concerning, that we don't know these things.
Thanks again for the great talk. I think this is the end of the workshop. Thanks again for every participant, including speakers, organizers, and attendees. And that's all. Have a great weekend. Thanks.